So EXA2CT is about solvers, programming models, and proto-apps. And in the present, or in the title, I put at Exascale. And I removed the Exascale because really the ideas that I'm going to present, they're not Exascale specific. So a lot of these projects are Exascale is, in my personal opinion, is a buzzword. And as Erwin already said, you really need an evolutionary approach. And then because a lot of the questions I get, like, okay, are these techniques also useful not at Exascale? Or, of course. So please use the ideas and don't be afraid if you're not. They'll be a lot useful also not at Exascale. So there's exascaling again, but let me give you an idea. But start by giving you an idea why scaling is hard. So we took this application. So we have a scientific and industrial board, which are industrial partners that give us access to their industrial applications. And this is an application from DLR. It's called Tau. It's a CFD proxy. It's a CFD application. And in current context, they're running this on their supercomputing, and they have about 50 million mesh points. But we see, for example, in Formula 1 CFD applications, that they're already using much more. They're up to 500 million mesh points. So we said to put this application into an Exascale context, let's assume we have 500 million mesh points. And then, so this from the application point of view. From the computer point of view, we see that computers will get more parallelism, and some of this parallelism will be in the context of many more cores. So in the order of magnitude of 10 million cores, but although you have many more cores, the amount of memory won't scale that much. So it might be that even you have per core less memory. So what does this mean for this specific application? That for a certain way of subdividing your mesh across your cores, you have many more fewer mesh points per core, which means you have much more mesh points in your application that are on the boundary condition, on the boundary of your cell that is allocated to that core. So this will put a lot more stress on your application because you'll have a lot more communication versus computation than what you have now. So we took this situation, we extracted the relevant portion of the application, and we put this into something called a proxy or a proto-application. And we looked at how does this proxy application scale, how can we make it scale better, and then how can we put what we've learned back into the real industrial application. So how does it scale? Well, there are many ways in which you can overlap this communication and computation. Because if you don't overlap communication and computation, because the application becomes so communication dominant, it won't scale it well. So there are many. The key point is there are many different versions. So this is on a system with 4 Xeon PHYs. So up to 4 Xeon PHYs, you'll end up with maximally 250 number of cores. And as you scale up the number of cores, some of the versions scale well, some of them scale better. And we're investigating what are the techniques that you need to do to make them scale good. Without going into detail, let me try to give you the key points on what do you have to do to make it scale well. So if you look at the don'ts, a lot of the MPI techniques are bulk synchronous, meaning you compute and then you stop computation, you communicate. Of course, this doesn't work very well. MPI is not multi-threading friendly. There are some ways where you can, there are some modes in MPI where you can do multi-threaded MPI communication, but it comes at a significant penalty. So that's why in a lot of cases they're doing single-threaded communication, but this doesn't scale if you have so many cores, if you have so many threads. And the third bottleneck that we found is that MPI data types are becoming a significant bottleneck. It's related to the second one because it's related to the fact that these MPI data types are usually evaluated, packed, and unpacked. especially if you have complex data types in a single threaded way. So what is a better way to do it? What are the do's? Of course, yeah, that they correspond one-to-one to the don'ts, more or less. So GASPI, which is, as I said, co-developed in this project, also in other projects, is much more asynchronous. You can do a write and a notify, and the communication, it allows you much easier to overlap communication and computation. We were able to get more or less the same results on this proxy application with an MPI asynchronous send and receive, but it requires much more tricks. It's much less obvious to do this, how to do this well with MPI than with GASPI. You need to have not single-threaded communication, but thread-to-thread communication, and you need to have multi-threaded packing. So if you do this well, you'll end up more here. If you don't do it well, you'll end up there. So this already gives you an idea about what EXA2CT is about. So let me try to tell you the different parts of EXA2CT and then go over them one by one. So I already talked about these proto-applications, where we take an industrial application, we extract the relevant parts where we see problems in scaling, and then we use appropriate programming models such as GASPI, but I will also talk about Shark, which helps the programmer to write easier write applications at scale. And the third part where we work on is solvers. So a lot of these applications work on solvers, and if your algorithm doesn't scale, you might use the right techniques and the right programming models, your application won't scale either. So you need you need both the programming models and the solvers, and you need to test it on your real-life applications. So let me focus first on the solvers and what we do there. I'll show you some examples of what we're doing. It's by no means complete, but I'll show you how we change the algorithms and the solvers to make them better scale. So one example is a pipeline CG solver developed in the project. It's available now in the PETSI library. In this case, it's an example is a pipe CG. So it's a conjugate gradient solver, and the key point is we use the programming models, we use the asynchronous MPI or GASPI to better overlap communication and computation. So we rearrange the mathematics, we rearrange the algorithms such that we can do in this case, the reduction, the inner products, in parallel with the SPMV, so the matrix multiplication. And this, as you see, it squeezes the total time of your application, because the total time of your solver, or at least of one iteration of your solver, because you're overlapping communication and computation. Another thing is avoiding reductions. So I'm not a solver expert, so don't ask me any nasty questions about this. But this graph shows, so the people of this, working on solvers in this project, they are investigating what is the effect of avoiding some of the reductions in your solver, because reductions in your solver are very communication intensive. They are very latency, they impose a latency penalty. So if we do only selective deflation, if we only do selective reductions, we can significantly make solvers that scale. You can make solvers that significantly scale better. So one of the examples is the top one is so this is the standard CG solver, and you see after the number of you scale to a certain number of MPI processes, it stops you stop seeing any speed up. While if you use selective deflation, you see that the black curve, you see that it scales much better. This is a second example on the work on solvers. And a third example which I want to give is resilience. So we also work on making solvers from an algorithmic point of view much more resistant towards faults. We want to make more fault tolerant. For example, so solvers, they solve a system of linear equations. If you lose a node in your cluster, it means you lose you lose part of the system which you're trying to solve. You lose part of your solution. And what we do is we have techniques. We don't lose the complete solution at that point. We'll only lose part of the solution, and we recover that part of the solution by solving a much smaller system of equations, by reusing what we still have at that point, which is, but we make sure that it's adapted for the type of solver that we're using. And what you can see is that if you, for example, if you don't do anything, you just initialize the part that you lost with zeros, you see that your convergence of your solver almost stopped converging, or the convergence of your solver it takes much longer. So the black curve is when you don't have any faults, while if you fix the fault that you had in an intelligent way, you can make your solver converge in a more in a way which is not as fast as if you don't have a fault, but better. So these were some examples about solvers. Let me now give you some examples about programming models. One thing which I want to introduce you is, which were already mentioned before, is this Gatsby PGAS language. And one of the benefits compared to MPI is that it's designed to be much simpler. So in fact, I'm a user. I'm not a developer, but to me, you only need 3 functions. You need a write, a Gatsby write, which basically says, start copying this piece of data, which is local, to another node, in my memory, to another node in another node's memory. And it does this completely asynchronous. So the function just starts the process. Gatsby write, and then you do several Gatsby writes, which means the data is flowing from your node to other nodes. And then you do a Gatsby notify, and you're guaranteed that the Gatsby notify will arrive at the remote site after all the writes have arrived there. So this is a mechanism to do a lot of things asynchronously, but still to have a certain point of synchronization where you know, okay, now I know that I have this data. And then there's the equivalent function on the receiving side that can wait for the notification. So you have a write, a notification, and a wait for notification. That's basically all you need, and it's really Gatsby is designed to make it to be very simple. It's thread safe. So you can do thread-to-thread communication. You can have multiple Gatsby communications going on from different threads. It's, as I said, it's globally asynchronous. And one of the nice things really is that it's interoperable with MPI. So let me explain this by why is this nice, by going to the next slide. So the next slide, so it's Gatsby GPI, you have these 3 functions, but it's still quite low level. And what we believe in the project is that for a certain subset of applications, namely in this case, applications that work on regular grids, you can create a higher level of abstraction that makes it easier to program your applications and make sure that your applications scale. So usually what you have is you have your application which is running on your cluster, and you're using a combination of MPI or Gatsby or MPI and Gatsby with for the internodes communication. You're using OpenMP, TBB, or pre-threads, or any of those combinations for threads, and you use some PETSI library or Patus stencil compiler library. And you need to make sure that you use the right combinations and that all of these things are interoperable, and you use the right compiler switches. And because it's a pain in the ass to really combine the right mix of all of these things. So what we try to do is we have a Shark library, which is a library for these regular grids, which is in between your application and all of these other libraries. And I'm actually working on this, and I spend a lot of my time making sure I use the right compiler switches, making sure that this OpenMP and MPI are interoperable, and making sure that it does the right techniques at, for example, to ensure data locality, and hopefully it makes it easier for the application to use in an efficient way all of these techniques that are underneath. I'll show you some examples later how this works in the project for solvers. So, but what I was talking before about interoperability between GASP and MPI. Actually, in Shark, some of the things are easy to do, are easy to give you good scaling in GASP because of the asynchronicity, but some things are much easier to do in MPI because MPI has a much more wide range of functions. You can do much easier to do gather scatter, much easier to do accumulations. So I use, whenever I feel appropriate, I use GASP, and whenever I feel appropriate, I use MPI. And the application library doesn't need to know about this. They don't need to know what's underneath as long as it scales well. So that's the idea. It's relying on, so the Shark library, which is the thing in between, it's relying on C++. I'll show some examples of this later. You have all sorts of, you have your multi-dimensional array, which is distributed across your cluster. So Shark, the basic data structure is an n-dimensional array based off whatever data type is in C++. Okay, I'll stay there. Don't worry. So, and then you have all sorts of operations on the multidimensional array. You have matrix products, you have stencil operations, you have these reductions, all the things you need, for example, to create the solvers that I talked about earlier. So these are the computational functionality. There is also communication functionality in the library. Typically, if you're, for example, for a CFD application, you do computation and then you do neighbor exchange. So we have communication primitives in Shark to do neighbor exchange. We have communication primitives in Shark to do reductions. And thanks to the C++ operator overloading, thanks to C++ expression templates, it still looks readable when you look at the code. So let me prove this by showing this. So this is work that actually where we combine work from solvers in the solver part of the project. This is an example where you use Shark to implement the solvers, and I will show you later that this also can this work on solvers is also connected to the proto-applications. So, but what's on the slide? So on the left-hand side, you see what a mathematician would normally write if he would write down an algorithm for a solver. This is a simple CG solver that the mathematician would write down on his slide. And if you would implement this in the Shark library, you get the thing on the you get the thing on the right. And you see the point here is there's almost a one-to-one mapping between the left-hand side and the right-hand side. The difference, of course, that the left-hand side is mathematics, and the right-hand side is then running on your cluster. It's so the star is actually translated to a multiplication or a stencil operation on your global array, which is distributed across all the nodes. It makes sure the data locality is all right. It uses we make sure that the vectorization is okay. We make sure that we use the multi-threading. So it scales quite well. So I have some slides if you want, but I didn't put them in the presentation. So the code on the right-hand side, it scales quite well. We're currently doing experiments where we compare the Shark type of implementation of a solver with the PETSI, and the results are preliminary, but it seems to work quite well. Okay, almost there. So the third thing the third aspect in the project which I didn't talk about is the proto-applications. And there, what we're trying to do is we take industrial applications from our industrial partners. They're not inside the project, they're inside an advisory board. And here are some applications, here are the applications that we use inside the project. So they range from CFD applications, combustion, This is a climate modeling to modeling application, machine learning, multiphysics. And what we do is we talk to the partners, and we extract the non-scaling parts from that application, and we make so-called proto-applications. But of course, the important part is that not that we create the proto-applications and we show that they work well and they scale nicely, but of course, we also want the things flowing or information or programs flowing the other way around. So there are already quite a number of examples where the things we did, the solutions we created in our project are taken up by our industrial partners. So for example, for the Oasis climate coupler, we worked on startup times. So startup times, when you scale out to many nodes, the startup times of your application can become really, really high. So we worked on that, and this is now one of the people in the project worked on this, and this has been taken up now by the application itself. For the Elmer code, we're starting a collaboration between two partners in the project, Intel and IT4I, and the developer of this Elmer application, and they work with three partners, work together to optimize the application. There have been open source applications based on the Ether applications. There have been open source, and there's the PhD student that was doing the optimizations inside the EXA2CT project now moved to Dassault Aviation and is implementing what he learned in our project in the company. Another case where I mentioned, what I can mention is that this proxy application based on the CFD application in DLR, there the people of DLR are now using GPI and GASPI inside their industrial application. So there are there are already quite a number of applications or results that have flown back from the project to industry. To what can we do for you? So as I said, go to our website, and we have provided the link to the open source solvers that are now in PETSI, which are using this pipelining. You can download GPI, which is an implementation of GASPI or Shark from the website. As I said, there are a number of proto-applications that have been made open source. And if you have an application, you can talk to us, and we can look at your industrial application and see what are the problems there to getting it scaled. So go to our website and have a look. And with that, I would like to finish by thanking the people of the project, because I'm standing here, but it's a work by 9 partners from all over EU. And I think one of the nice things about this project is that the people really work together. So we wouldn't have achieved this without the people of the project actually working together. Thank you.